All right, I'm on. This is work with Robert Carr, also one of Balish's former students who's at University of New Mexico. He sends his regrets. And this is stuff we've been doing with the traveling salesman problem. Everyone's favorite problem to work on, I know. Let's see. All right. So how does the graphical traveling salesman problem differ from the regular traveling salesman problem? In the regular traveling salesman problem, you're assuming a complete graph underneath, and you're trying to visit every node exactly once. In the graphical traveling salesman problem, you have a graph that's not complete, often very sparse, and so you may not be able to visit every node exactly once. You may have to visit nodes multiple times and visit edges multiple times. So you just have to visit each node at least once in the graphical traveling salesman problem. You can, of course, convert the graphical traveling salesman problem into a regular problem, although that might increase the complexity on the edges from order V to order V squared. So as long as we have a sparse graph, can we take advantage of this and solve a problem without multiplying it by itself? So what we would like to do here is not only to find a good formulation, but find one with a tight linear relaxation so that when you relax the problem, remove the integrality constraints, you still get a good quality solution. And Bob Carr is convinced that there's a reference out there that references as an open problem for the graphical traveling salesman problem, but he can't find the reference. So we're looking for this reference out there. So if anyone knows of a reference about good quality formulations for the graphical traveling salesman problem, let us know. We're going to be focusing on the symmetric problem that assumes the distance from A to B is the same as the distance from B to A. So this is the standard traveling salesman problem, subtour elimination constraints, making sure that you cross every cut set, degree constraints, making sure you visit and leave every node exactly once, upper bounds, that you can only use each edge once, and of course the integrality constraints, which are relaxed when you solve the relaxation. The formulation for I should mention that these subtour elimination constraints can be separated in polynomial time, or they can be replaced by R.K. Martin's flow formulations or something based on that allows me to have a polynomial-sized set of constraints. For the graphical traveling salesman problem introduced by Cornelius von Lupton-Nedef in 1985, we have a similar looking thing, but a few things that are a little bit different. I have to worry about subtours of size 2 because I could go back and forth on the same edge. This is the big problem. I've got constraints that say the degree is positive and even, which makes for a lot of disjunctions, which are messy to deal with. There's no upper bound on how many times I can visit an edge. Now it turns out if you just use a lower bound of 2 for the degree, you get a pretty good quality relaxation. And it was also shown that if all of your edge costs are positive, you can use 2 as an upper bound. And that's what we're going to assume in this problem, is that we have positive costs, so that 2 upper bound on using an edge is going to be important. The thing we can notice about this problem is that often you may have intersections between your destinations. So if you imagine a road network and you want to go from Pittsburgh to Philadelphia, there might be a lot of intersections along the way that are not destinations. And the paper of Gordon-Jules von Lupton-Nedef called these nodes Steiner nodes. And so we're going to use that same language for these kinds of intersection nodes. So here's the formulation when you have Steiner nodes. The degree constraints are positive and even for destination nodes. They are simply even, possibly 0, for the Steiner nodes. And you have to make sure that each cut set that contains a destination node on each side is crossed. All right, only sets containing destination nodes must be connected. Steiner nodes may have degree 0. Okay, since positive edge costs lead to an upper bound of 2 on each edge variable, here's where things get interesting. Let's define 2 new variables, y and z. Y on an edge is 1 if I use the edge exactly once, and z on the edge is 1 if I use the edge exactly twice. So if the x's are going to be integer, these are the only two cases that are possible. And so we get an expression for xe in terms of the y and the z. And we have a new constraint we can use because we can't have both y and z be 1. And if we're trying to find out if a node has even degree, only the y variables matter because the z variables contribute an even number to the degree. And this allows us to create degree constraints that don't get messed up by the fact that the value of xe could be 2. So here's how we do this. You have to create for each set of neighboring edges of a node that is odd, this constraint here. So the ones selected by the set versus the ones not selected can't be 0. So, let's see, I have a picture, not here. So I want this to be the case to force not selecting an odd set of edges for which y should be 1. And this will be exponential in the degree of the node, but if we're talking about a sparse graph on a highway network or a road network, these tend to be small. So this maximum degree in these graphs tend to be in the neighborhood of 4 to 6 for road maps, 5 to 8 for highway maps. So this exponential size in that small constant turns out not to be an obstacle. We can still solve these very fast. And again, what makes this work is the fact that we don't have variables whose potential value is 2 anymore. We've dissected the odd part and the even part of xe so that we can make this constraint work for all the odd sets S. Now let's relax and see what goes wrong. And yes, things can still go wrong because if the solution wants there to be an odd degree node, well, it'll just set z equal to 1/2 along a path. So that doesn't help unless we find a way to take these kinds of paths out of play with some more constraints. Because this is still not helpful if I have z equals 1/2. It's as if that was y equal 1 along that path. So here's the clever way we can prevent this. I know it's a weird looking constraint. Again, the x's are sort of shorthands for that y plus 2z. But this ends up being the subtour elimination constraint for ij if z is 1. It ends up being the lower bound of the degree constraints if z is 0. So as long as I and j aren't Steiner nodes, this new constraint is valid. And if I try to create a half z path along that edge, that left-hand side ends up wanting to be 3. So I've effectively cut this off using constraints that assume an integer value of z. And this is very useful. However, again, it only works when I and j are not Steiner nodes because the degree constraints don't assume a minimum of 2 for non-Steiner nodes. So let's get rid of the Steiner nodes. So we take our graph and we look for all the shortest path pairs, and if any shortest path pairs don't have destination nodes in the middle, we create a new edge in the graph. And this will create a Steiner-free graph representation, and in practice, this actually lowers the number of edges, not increases. I think in all but one of our instances, this actually lowered the number of edges in the graph. And for the one that it increased by about 2 or something like that. So this has not made the problems more complex by removing these Steiner nodes so that we can now use these constraints. All right, so now let's talk about the numbers. This is a map of the interstate system of the US. Yeah, if you want to play with this data set, it's right here. I'll get out of the way in case you want to look at that. But anyone can use this data set they like. I find it very useful just to do problems on. I have a variety of degree 1 nodes. I've chosen some edges to put intermediate nodes on for important locations, so I could do things like state capitals as sets or state parks as sets. So this gives me a good playground, 216 nodes, 358 edges, a maximum degree of 7, to really play with these formulations to see, does this in fact tighten that gap on these instances? So here are a bunch of instances we created. So I choose a subset of nodes. I take all the nodes that are in shortest paths between those nodes, and that makes a problem. So the number of Steiner nodes is in parentheses for each of these cases. In some cases, I chose very clustered nodes with almost no Steiner nodes. Other cases, I chose a very spread out set of nodes with lots of Steiner nodes to get a good variety. I do have the entire graph on here, and this is the integer solution for the TSP on that case. So let's look at some of these results here. So here's an example I made. This one I just wanted to test to make sure our routine was working, because our routine is supposed to completely absorb the integrality gap for this problem that has that size 3 path between those 3 paths. And yes, it did work. Here's another small example. This is 29 destinations of NFL cities before the Oakland Raiders moved to Las Vegas. Maybe I should update this sometime soon. Yes, and there could be some future movement later, I know. Yes, Bob Carr grew up in Pittsburgh, so he's a Steelers fan, and I grew up near Philadelphia, so I'm an Eagles fan. So these are all, and this red is the optimal solution for if you wanted to visit all 29 NFL cities. That is the best way to do it along interstates. So let's see how we did on reducing the gap. So I'm expressing the gap here as a percentage of the optimal solution. So if I just take the ordinary formulation from Kornagels, von Lipton, Nadef, this is how small the gap was, and whether I use ours with the Steiner nodes or without the Steiner nodes, in most cases I found a small improvement. In some, as much as 1/3 or even near 1/2 of the gap was completely done. Again, the first example was pathologically made as a test to make sure we would close the whole gap. But I do see there are a couple instances where there's no help being gotten, but in a lot of these cases, I'm making a significant step into closing that integrality gap. And we did notice that there is a pattern to when the gap is likely to close. So if the solution to the problem had a lot of z variables, so anytime the x variable is positive, what percent of those variables was the z variable also positive? If that number tended to be small, then there was no improvement gained by our formulation. However, if the instance by its nature had, for whatever reason, lots of z edges, then we did find quite a bit of improvement, and that magic number seems to be around 10%. I don't know whether that's unique to this instance or common to all instances, but at least on this individual problem, I'm working on making a formulation on the European highway E model so I can run some bigger test data and see what happens there. But it looks like that I've made an improvement on problems where there seemed to be a fair amount of z's, so 10% to 20%. When I have a z range in there, I seem to be able to close the gap by more. So that was the accelerated version of this talk. I have added the Canadian cities just to see if that would change anything. It didn't. But if you want to add the Canadian cities to the instance, I believe that's also available on the website. That brought me up to 410 edges. And the degree of Montreal is actually degree 8. But I'm happy to answer any questions on my accelerated talk. All right. Sure. Running time for all these was 5 minutes or less, but of course these aren't huge instances. So I really wasn't concerned about are these running faster. I wanted to know, did we get a smaller gap? But all of these instances ran very quick.
follow-up question on that. If you were to embed this in a branch, Katan branch, how would they behave? Different formulations?
I haven't tried that. So.
Okay. Any further questions? Okay, let's thank you.
Okay.